Hi everybody, welcome back. So today we're going to talk about missing data. When I was in graduate school, I was trying to run a regression, probably maybe the first time or one of the first times. Not the first time ever, don't give me that. But the first time for me. I was running it on American National Election Studies data. And as you know, when you analyze a survey, you spend quite a lot of time writing recodes. And so you'd recode the data in terms that you could put it into the regression. Something coherent so that up means the same thing and the numbers all are coherent. And then I realized that there were that when I ran the regression and I looked at the results didn't make any sense. And I thought, well, what the heck's going on? We're supposed to know something about American politics. At least that's what they were teaching us in school. Anyway, so I look at the data and I realize, all the missing data when someone refuses to answer the question are coded as -9. And my other numbers didn't make any sense, right? A -9 wasn't part of the scale of the original variables. It was just an indicator to the analyst, like, don't treat this -9 as the other data, which of course I did, and that's why the results didn't make any sense. Okay, so then all I have to do is just do something with the -9s. But what am I supposed to do? And they didn't teach this in my class, so I went to my textbook, and I'm flipping through the textbook. There's nothing about missing data. So, I didn't even know what to call it. But I'm looking through it, I couldn't find anything. So I went to the computer program. It was SPSS, it was version 9, the cover was maroon, I remember it vividly. Anyway, so I pick it up, I look in the index, and I finally find something about missing data, and it says listwise deletion. So that means I go to that part in the big fat manual, and I'm looking through the manual, and I find listwise deletion. And listwise deletion says if any observation has any missing data, it just deletes it. Great. Okay, so that's the method, that's the methodological procedure that you use to deal with missing data. So I thought, well, I'll use that procedure. So what you do is in SPSS, you recoded the -9s as missing. So that's what I did. I recoded them as missing, reran the analysis, and I didn't have any data at all. Like there was no data, because every single person I had a lot of variables in there, probably too many, and every single person had at least one value that was missing on one variable through the whole data set. So that was crazy, because then they were throwing away, the computer program was throwing away a huge amount of information, because if somebody answered 60 questions and didn't answer the 61st, we just threw away the data. So I thought, well, that's no good. So what am I going to do now? So then I looked at the partisan identification question, which ranges from strongly disagree to, which ranges from, let's just make it Republican, Independent, Democrat. They break up the Republican into strong Republican and weak Republican, and Democrat into weak Republican and strong Republican. But in any event, I had a -9. I didn't want to throw out that observation, because there was informative information on all the other variables that respondent had given us. So what are we supposed to code it as? So I thought about it and I said, well, I'll code it as independent, right? Why not, right? And then I got to keep that observation. And I followed the same rules for all kinds of other things, okay? Now, of course, I'm basically just making stuff up, right? Now, it's not crazy, but it's not right. And in any event, even if it is right, the computer program thinks that the respondent gave that answer, right? And so at best, the uncertainty estimates are going to be completely wrong, because I obviously don't know an answer that I just made up, rather than a better or as well as the answers that the respondents actually gave, right? So that's sort of crazy. So that always bothered me. And then I came back to missing data. Okay, so we're going to introduce a better approach to deal with missing data. I'll give you a little bit of an overview. We'll talk about multiple imputation, which is going to be a relatively simple way of pre-processing the data, quite like matching. It doesn't work like matching, but the same style where we pre-process the data by filling in the missing values in a specific way, and then we analyze the results in a way that's very consistent with what we would have done previously in our modeling analyses. So it'll be very convenient. But we'll also talk about other methods. So we're going to start off with the missingness assumptions, the assumptions necessary to use the different models necessary to deal with missingness. Then we'll talk about building application-specific methods, where we tune the method to the specific problem. It's harder, it requires more thought, it can be very valuable, but it requires lots of effort. We did this once already with the exponential censored regression model. So that gives you a feel for how to correct for one type of missingness, which is censoring. But we did it in the context of just duration data and just the dependent variable. Right. Multiple imputation, in the way that we do it, will deal with missingness scattered throughout your data matrix, in the dependent variable, the explanatory variables, everywhere. Multiple imputation requires multiple equation modeling, which we just went through, and so that's great. It will require some different computational algorithms. We'll learn about those. There's software to implement all of this, so you needn't worry about it, but you might want to get a feel for it. We'll talk about what can go wrong, and we'll talk about how to extend the models from the usual approach to the usual data set we use for missing data, which is survey data, to other types of data like time series cross-sectional data. Okay, so let's get started. All right, so here's just a quick summary. There are plenty of approaches to dealing with missing data, like the ones that I used in graduate school, that are biased and inefficient and have all kinds of other problems. Probably the chief method of dealing with missing data is just making numbers up, like the changing party ID one I gave you the example for. There's list-wise deletion. In 2000, I did a little content analysis with my co-authors, and we found in the major political science journals, 94% of authors were using that method, so it was pretty common. It's not so common anymore, but it's still relatively common. There's lots of other ad hoc approaches, some intuitive, most biased, and so we'll talk about some of those, but we'll have to have a feel for it because you might have questions about any one of them in particular. We'll then talk about application-specific methods, which are efficient and model-dependent, but harder to use. And then we're going to talk about multiple imputation. So let me just give you one quick overview of what multiple imputation is. It's easy to use, statistically appropriate. And the idea is you take your data set. You don't want to fill in one value for every missing, your data set basically is Swiss cheese, right? So then you want to fill in the holes. Now, if you fill in the holes by just guessing, well, if you guess right, then that's good. But if you guess wrong, it's not so good. But even if you guess right, your standard errors are going to be wrong if you tell the computer program that you know the values you made up as well as the values you didn't make up. So what multiple imputation does is it takes the data set, it uses a special procedure to fill in the values, and then you take this completed data set and you put it over here. Then you take the Swiss cheese data set again and you fill them in again and you put it over there. And you do that 5 times. The values that you impute, that you fill in the holes in the Swiss cheese, differ across the data sets. They differ more if you can't predict the missing value very well, and they differ less if you can predict it very well. That reflects the uncertainty. This is very convenient because then you take the completed data set and you analyze it the same way as you would have originally by applying the statistical model, writing down the likelihood function, optimizing the likelihood function, simulating from it, conveying your quantity of interest, all the usual things. It's very convenient, and then you combine the results in a specific way from the 5 data sets. So it's quite easy to use. It's also pretty robust because you're separating the missingness component from the analysis model. And the advantage of that is that you model the two separately. If you modeled them all together in one gigantic multiple equation model, sometimes that's the right thing to do, sometimes that's advantageous, but if you do that, and you get something wrong in one part of the model, it can affect things in the other part of the model. So model dependence and sensitivity and what we're calling non-robustness can affect all of that. Okay, so in order to tackle this problem, my co-authors and I and my former students went after this problem and built some relatively simple, some of the approaches that we're describing. So in this first paper, in the American Political Science Review, it's almost 20 years ago now, it's with James Honecker, who was who is a research scientist at SEAS and is moving to Facebook, and Joseph now Ann O'Connell, who was also in this class. All three of these were in this class. And Joseph is now a professor at the Stanford Law School, and Ken Sheevy is a professor in the Stanford Department of Political Science. They're terrific. There's another paper that James and I wrote in the American Journal of Political Science about how to apply missing data to time series cross-sectional data. We'll get to that towards the end of this lecture. Matt, along with Matt Blackwell, we extended these methods to deal with not only missing data, but you could think of it as partially missing data, which is missing data with, what we think of is that there's fully observed, absolutely correct data, and then there's the holes in the Swiss cheese, which are absolutely unknown. But in fact, there's things in the middle, which is we have an observation, but we know it's got error in it, right? And so Matt and James and I worked on extending these problems, these multiple imputation methods, to missing data. And we came up with a method called multiple over-imputation. And this is actually two separate papers that appear one after the other in Sociological Methods and Research. Okay, all of these are implemented in a quite easy to use computer program called Amelia. It's now Amelia 2, a program for missing data. Amelia is named after that famous missing person, right? Okay, so all these are available at this website, which is also my website, just a particular page of my website, garyking.org. All right, so now we're going to focus on missingness assumptions. All right, these are the assumptions necessary to build certain types of models for missing data in all kinds of statistical analyses. Let's start with some notation. Let's make D our entire data matrix, not the X's, not the Y's, but everything, okay? And let's imagine that all the values of D are there, right? But some of them, the blue ones, we don't actually see, okay? For whatever reason, maybe they're values that governments didn't provide, or they're survey respondents that just refused to answer the question, or whatever it is. M is just an indicator matrix for blue, black, right? So if it's a 0 if it's missing, and it's a 1 if it's a 1 if it's observed. The key thing here is that the missing values, which are blue, do exist. Okay, those values do exist, but we just don't know them. It's very important that they actually exist. Okay, we're going to combine all the missing values, and we're going to call that dmiss. So all the blue values together, we're just going to put a little subscript on D and call that dmiss. And then all the other values we're going to call dobs. So D is equal to dmiss and also dobs. If you treat some elements as missing, make sure they exist. I just said that, but I'm saying it a second time. And the reason why is because when we submitted our first paper for publication, they liked it, but they said, you know, these values that you're imputing have to actually exist, right? And of course, it was in the paper. We said it in the paper. And the revised version, they said it again. So they made us put it in the paper multiple times. So I'm saying it multiple times. And the way that I try to get people to think about it is I ask the question in class. Obviously, I don't think you're going to answer the question right now because you're nowhere near me. In any event, I'm going to ask the question, what's your view on the National Helium Reserve? And of course, nobody knows anything about the Helium Reserve. Until actually, as a side point, I gave a talk at Wesleyan, and everybody normally understands this question because nobody really has an opinion on the National Helium Reserve. But when I gave that talk, and I used the same line basically, the entire front row stood up and applauded. And I said, who are you people? And it turns out they're physicists, and that's their issue. Like, they care about the National Helium Reserve. In any event, the question, all questions are of interest to some people and not of interest to other people. And if I ask you about the National Helium Reserve, at least before I told you that the physicists cared about it, my guess is you didn't have an answer to the question. If you said, I don't know the answer to the question, I don't think it's reasonable for me to say, you have an answer, but you're not willing to tell me. I think it doesn't actually exist, and therefore it wouldn't be reasonable to impute a value for your missing value. On the other hand, if I say, what's your income? And you say, I don't really want to tell you. Or even, I don't know. That's not true, okay? Well, it may be true that you don't know, but it is the case that you have an income. No matter what, you have an income. It may be small. It may be really small. It may be even below that in graduate student level. But whatever it is a value. It is a number. Everybody can be imputed an income, but everybody can't be imputed the answers to survey questions about interstate banking or whatever it is. Okay. So if some values don't exist, let's just think about this as an aside. So suppose they don't exist. What kind of analysis would you do, right? It's worth thinking about that, because you would not do this analysis. You would not impute the values. You would not fill in the values if you don't have a view about the questions we're asking you. So suppose we actually were analyzing data on the National Helium Reserve, and all the physicists actually gave a good answer, and other people had NA, just no answer. How would we analyze those data? Okay. I mean, that's a good question. We wouldn't use multiple imputation. We wouldn't use missing data. It's not missing. But what we could do is we could code the variable as NA1 and not NA. That is, they answered the question as a 0 or vice versa. And then we could try to predict that. That would be interesting, because the indicator matrix for whether it's observed or not is fully observed, right? So on the right-hand side here, is the missingness matrix. That missingness matrix is always observed. We always get to know whether an observation is missing or not. And in the case of variables that don't actually have answers and can't be imputed, you could actually analyze who answers the question, and that may be of substantive interest. Okay, so missingness assumptions. The literature here has insane names, so you just have to deal with them. We're gonna start with, I'll just show you the first two names here are missing at random and missing completely at random, and I always want them to, like, why don't we have an assumption missing absolutely completely at random? In any event, just ignore all that, okay? The first line, which I'm gonna go back to, is missing completely at random. So MCAR, and the idea here is the M matrix. That is the matrix of zeros and ones for whether or not an observation is observed, the missingness matrix, can be predicted with nothing, right? So if you flip coins to decide whether you're going to answer questions, that's missing completely at random. And that's basically the model. The model is, it's just random. It's not a function of any systematic component or any explanatory variables. That's a very optimistic kind of assumption. It's probably not true, but it is one possible assumption. A more sophisticated assumption is what we'll call missing at random. It should probably be called, missing completely random should probably be called missing at random. Missing at random should probably be called missing at random conditional on the explanatory variables, or missing conditional at random. In any event, MAR, the idea here is that you can predict M, the missingness matrix, which people answer which questions, as a function of the observed values in the data set. That's missing at random. You imagine we could do some analysis with that. There's another level here, which is called non-ignorable, another sort of crazy name. But non-ignorable, or NI, means that you can predict M with, potentially randomness, which means nothing, but also the observed values and also the missing values. So the missing values themselves that you don't see, those blue values on the previous page, those blue values may indicate whether or not you answer particular values. So let's do the same thing again so you have a better feel for it. So MCAR, missing completely at random, we can think of as naive as a statistical assumptions. Coin flips determine whether you're going to answer a survey question. Probably not. Usually something's going on. Mathematically, this is the way we're going to write it. P of M, the missingness matrix, given all the data, is just a function of, is not a function of D, and therefore we can drop D and it's equal to P of M. So that's the idea. So it's just a function of basically randomness. MAR, which I would think of as an empirical assumption, it's an optimistic assumption, but it's empirical, is that missingness is a function of things that we can measure and did measure. That's great, and the way we're going to write it down is P of M given D is equal to this, because I'm just breaking the D up into D obs and D miss. But then the key assumption here is that we can drop D miss. Okay, so that's what goes on in this last equal sign. We drop D miss, which means that MAR assumes that those blue values, the true values of the missing data, are not necessary to predict which people answer which questions and which questions are answered by which people. So independents are less likely to answer the vote choice question with partisan identification measured. Or some occupations are less likely to answer the income question with occupation measured and used as a predictor. Okay, so that's the second approach. It's an empirical approach. It's the one we're going to focus on. There's another one which we have to be wary of, and we call it fatalistic, because if it's true, we're cooked unless we understand it, we pay attention to it, and we correct for it. And the idea is missingness depends upon things that we do not observe. It depends upon the blue values. And the idea here is P of M given D doesn't simplify because it's a function not only of D obs, but it's also a function of D miss. So for example, we might have income censored if income is greater than $100,000, and we can't predict income with other variables. So you can't predict it with occupation, you can't predict it with other variables, maybe because you didn't put in enough other variables in the data set. Okay, so it might be, for example, if you do a survey and you only ask income, and people who are wealthy choose not to answer the question, then that's non-ignorable. If you add variables into the regression, like occupation and house, the value of the real estate that the person lives in, and how much money their parents had, and all kinds of other things that can predict your income, then that will turn an NA problem into an MAR problem. So instead of assuming NI, you can assume MAR, and we can do something about it, which is really great. Now we're going to talk about existing general purpose missing data methods to give you a framework for how the literature deals with these things, so that when you see people in the literature using these things, don't trust that article quite as much as the author is claiming, at least potentially. List-wise deletion. Now I've told you what list-wise deletion is. If any one cell value in the row of the data matrix is missing, you throw away the whole thing. Now, obviously, you're throwing away a lot of information. And the question is, if one value is missing and 60 or so are observed, then there's a real question as to whether you're risking more by imputing that one number as a function of all the other data. That's what we'll be doing. Or whether so that might create bias because you may impute it wrong, or throwing away the 60 values which you know for sure, which might and the whole observation, which might create selection bias. So it's a call. It's not always as obvious as I'm trying to make it out, but it is a serious decision. List-wise deletion. So what we figured out was, let's suppose MCAR applies, which is basically the best case for list-wise deletion. What happens is the root mean square error is off by about a standard error. And if you think that, roughly speaking, we want to get our coefficients up twice our standard error so we can say they're significant or something like that, and you lose one of those just from choosing list-wise deletion, that's really bad, okay? If the missing data process is MAR, then it's biased. By the way, where did I get the one standard error? Well, it depends upon how many observations you lose in practice. And what we found was most articles would lose about a third of the observations. People who tried harder wound up losing more than half the observations. We picked the people who wrote articles at a methods conference. So those are the people that knew how to analyze data, but at the time, before widespread usage of missing data, they were, what would they do? They would focus on other methodological problems like omitted variable bias. And if you think about omitted variable bias, you control for more variables, but any one of those variables could have a missing value. And so the more you controlled for other variables, the more observations you wound up losing. So listwise deletion is not a great way to go. You can do best guess imputation, which obviously depends upon the guesser. There are attempts you've seen that you may see in the literature where people will add a zero whenever you see the hole in the Swiss cheese, and then add an extra variable, which is a 1 or a 0, 1 if you've imputed with a 0 and a 0 otherwise. And it sort of feels like maybe that would correct it. It's biased. It's been shown to be biased. There's pairwise deletion instead of listwise deletion. You might find this in computer programs, and occasionally people will use it. The idea here is that regression in particular, and some other techniques, you can take the data set and first summarize it with a full covariance matrix, sample covariance matrix of all the data. Well, if you do listwise deletion, but only for each pair of variables at a time, then you can fill in this matrix little by little with as much data as available. That's true, except the whole variance covariance matrix might not be invertible. Your data set is based upon your analysis is based upon different subsets of the data for different purposes. So it's hard to make it a really coherent method. There's hot deck imputation, which works quite like matching. What you do is you imagine this. You have one observation missing and a whole bunch that are observed. And then you look for another observation in the data set that has all the observations observed. Then you can use that in order to impute the missing data, you can take the observed one from the matched observation. It's sort of a good idea, but it's very inefficient in this context because it's hard to find matches. You could do similar things that we talked about in matching and find similar observations, which could potentially create bias if they're not similar enough. But either way, no matter what you do in this case, your standard errors are going to be wrong. Because after you impute that single imputation, you're going to wind up with telling the computer program that you know all the imputed observations just as well as you do the observations that really came from the data. And so it's a clever idea. It's used, sometimes the Census Bureau uses it. There are other approaches. And sometimes it may work for you. But, but the standard errors for sure would need some fixing. There's mean substitution. Let me show you what mean substitution is. So let's take the left graph here. I will show you like that. So if you look at it like that, I'll do this. Okay, I have to use all my toys at least once. So if we have x horizontally and y vertically, and this is all the black dots are a scatter plot of the points that we observe. And now suppose there is a few points noted in red here where we observe x, but we don't observe y. So what do you use? Well, mean imputation, or mean substitution, and there's computer programs that do this. They're called mean substitution. Is whenever you don't observe a value on a variable like y, you just replace it with its mean. Okay. Well, what are those red dots going to do to that analysis, right? If this true red dot, if the red dot here, if y were observed, is up here, suppose this is the actual distribution of the joint distribution of x and y. If that's true, then these red dots belong up here, and these red dots, on the left hand end belong down here. So what you do is if you take some of the dots and you go and you make it that way, then what you're doing is you're attenuating your results. So probably not a good idea. If you only have one variable and you're willing to assume that the missing data are representative of the non-missing data, and you don't have any other variable to improve things, you can use the mean. But even so, the standard error is going to be wrong. We can look at the right graph here to do y hat imputation, which is going to be better. Let's think about that. So the idea here is when we don't observe y, instead of replacing it with the mean, like on the left-hand side here, we replace it with the regression of y on x using all the other fully observed data points. And then you just put them on there. This, however, doesn't mess up the regression, so it doesn't attenuate things, so it's better, but it's massively optimistic, right? So the idea is that for all the data points you observe, the points fall as a scatter around the regression line. But you're making the assumption that the points that you don't observe fit the regression line perfectly, okay? Now, there's no data to contradict your claim, but if there was ever an optimistic assumption, that's the one, and so your standard errors are surely going to be too small. You could go one more step and add, in the simulation sense, add the vertical variability here, and that would be a good idea. So instead of using the regression line, let's add the vertical, draw from the normal with mean equal to the regression line, x beta, and the variance equal to the estimated sigma squared. That's a great idea. But what does that miss? Well, look at what it's doing. It's doing y hat plus epsilon, but it's assuming y hat's exactly right. So what you really need to do is take the betas and simulate them, right? If you simulate the betas and put them in, that's estimation uncertainty. Then simulate the epsilons, and that's fundamental uncertainty. And that's basically what multiple imputation is going to do for you, except you can't really do it by hand this way unless you only have missing data in y. What if you have missing data in x? Then this doesn't work, right? So multiple imputation is going to enable us to run a regression of every variable on every other variable, and it's going to appropriately simulate estimation uncertainty, and then also fundamental uncertainty, and impute the values from all, conditional upon all the observed data that we have, and then reflect with the multiple imputations rather than a single imputation the full information that we have about the joint distribution of the variables. Okay, all right. So now let's talk about application-specific methods. So here's a brief overview. The examples include the censoring example that I've shown you already. There's truncation, where you take the dependent variable below or above some value. You just delete it, and you don't even know it exists. So the censoring value is missing, but it's censored, but that something happened to it. Truncation, the values that are truncated don't appear in the sample. There's likelihood inference, which are unknowns given knowns. And so it's the probability of some parameter theta given y-obs, given the observed value in the data. This is optimal if the model's correct, right? Because at least according to the likelihood theory of inference, obviously you should use the likelihood function. It can be model dependent because it's sensitive to distributional assumptions. It's often difficult practically. I mean, it's not that hard. We did it for the exponential censored duration model, but we have to do it for every model, right? So if you pick a different model, if you change models, you have to come up with a specialized procedure. Sometimes code exists, and that'll make it easier. There are application-specific methods available for scattered missingness through y and x are pretty rare. So they may solve problems in specific cases, sometimes optimally, sometimes better than multiple imputation, but they're more difficult because we have to tune it to the particular problem, and they don't exist for the most part. So it is nevertheless important to understand what these do, even if you use another approach, which I'm going to, for the most part, recommend. All right, so let's think about how we create application-specific methods. So suppose, again, D is broken up into the D-obs and D-miss, and it's fully observed. So it's not going to be fully observed because obviously D-miss is not observed. But let's imagine that it's observed for the moment, and then we'll correct for it. So P of D which remember we're making believe is observed, and M, which is always observed, can be factored into these two components. The joint distribution of the data and the missingness matrix is equal to P of the data, given the parameter, times P of the missingness matrix given the data. So it's always, you can always do something like that. That's a conditional factorization. So under what conditions can we drop the green missingness matrix probability distribution? What are the conditions? Okay, and the answer is we go back to our models for multiple equation models, and the rules are that there have to be stochastic independence. So D and M conditional upon theta and all the other variables or any other variables have to be stochastically independent. And also they have to be parametrically independent. So same exact rule as before. Okay, suppose as usual suppose now, as usual, that D is observed only when M is 1. So it breaks up into D obs and D miss, and D miss is not observed. And under likelihood, what we do is we integrate out the missing observations. So that's the likelihood. The likelihood is the distribution of P obs, not miss, and not D, and M. So this is equal to the same distribution that was factored over here, integrated over the D miss. So you basically just collapse over the dimensions that we don't see, and then we get the thing on the left-hand side here. So no problem. So we can write down what this thing would look like if we could do the integration, and that's what it would look like. Great, okay. And under the assumption of MAR, if we make the assumption of MAR, which is basically no parametric or stochastic dependence, the same thing as in the multiple equation talk, then this whole thing is proportional to D obs given theta, and we don't have to model this piece. Now that's nice because we don't actually spend a lot of time studying what causes people to answer survey questions or not. There's some studies of it, but that's not the main subject of our study. So it's nice that we can drop that under the MAR assumption. If the MAR assumption doesn't apply, then you're going to have to pay attention to it and model the two jointly. With MAR, P of D obs given theta becomes specialized to the particular problem. It's difficult if X is missingness, this thing becomes big, but there may be no help, or maybe that you've developed a specialized application-specific method that deals with the whole thing, but that's just a bigger lift, and you've seen this model. Without MAR, then the missingness model is not ignorable, and you can't drop it, and so you have to model it. I've already said that. Non-ignorable models, there are some. You may have heard of models of selection bias, Heckman selection models and things like that. They often don't do well because they are highly model dependent, and Jim Heckman recognized that recently, and shortly after he made that clear, he won a Nobel Prize for it, so good for him. Okay, now let's switch to multiple imputation. All right, so here's how it's going to work. The point estimates are going to be statistically consistent. They're going to be efficient. The standard errors are going to be either correct or they're going to be conservative. So they're never going to be anti-conservative, which is the responsibility that we have in science, right? So the idea here is we impute M values for each missing element. M is going to be bigger when there's more uncertainty and more missingness. So you might have to make M really big, but M could be small. The imputation method that I'm going to describe, we'll explain how it works, is going to assume MAR. The model has to include all of the estimation and fundamental uncertainty, and it produces independent imputations, that's part of the requirement. So we create M completed data sets. We observe data. The observed data are the same across the data sets, exactly the same in all the data sets, and the imputations of the missing data differ. The cells we predict don't differ much. The cells we predict well don't differ much. The cells that we can't predict very well differ a lot. thus appropriately reflecting our uncertainty in the imputation process. Then the great convenience here is after you do the imputation, for which there exists this computer program, Amelia, right? You just run the imputation, you throw in your data set, you get out 5 very nice completed data sets. Then you run whatever statistical model you would have run had you received the full data with no missingness at all. And there's an easy way to combine the results. So I'm going to show you that easy way right now. Actually, there's 2 ways. So the simplest, from a general point of view, is you just average. You take the point estimates from the 5 data sets and you just average them. If Q is the quantity of interest or an estimate of the quantity of interest, you just add up and divide by, by n. The standard error is slightly more complicated. You take the mean of the squared standard errors and add it to the variance of the point estimate across the 5 data sets. This is the within variability estimated by the standard error plus the between variability estimated by the variance in the point estimates. The green component there is a little bias correction that you need for finite samples. It goes away as m gets large, so it's not particularly important. Turns out this simple procedure can be made even simpler for us because we do simulation. Fits our procedures really well. So what you can do, it turns out, is ignore what I just told you on this page. And instead, if there's 5 simulations, draw 1/5 of this, excuse me, if there's 5 if m is 5 and you need 1,000 draws to calculate your quantity of interest with simulation, you draw 1/5 of those 1,000 draws, 200, from each of the 5 data sets, and then just put them together as if you had drawn them all from one simulation process and do whatever you were going to do originally. You know, make your inferences on the combined set of simulations just as you would normally. So this fits utterly clearly and easily into our procedures. Okay, so now we need an imputation model. So all we have to do, let's just think about this. All we need to do is figure out how to impute, how to fill in the missing data in an appropriate way following the MAR assumption. And then we put them together with simulation and then we're good to go, right? All right, so what is this? For starters, I'm going to imagine that D is complete. We'll correct that, of course, because the point of this is missingness, so D is not going to be complete. If D is complete, I'm going to use a seemingly unrelated regression model. And that's what we have here. So seemingly unrelated regression model, where D is distributed as a multivariate normal with mean vector mu, 1 mu for each of the variables, dependent and explanatory, are all in your data set, and the variance covariance matrix equaling sigma. That's a, k plus whatever by k plus whatever, right? Whatever being how many dependent variables you have also. This sort of seems crazy because there's no systematic component. The systematic component is constant. But it turns out that in this multivariate equation model, which is what that is, that's a multivariate equation model with constant systematic components, it will imply that if you're interested in the regression of one variable on another, it will imply it. In fact, the way to estimate a regression of one variable on others, you can calculate from this variance covariance matrix and this mean. So all you need to do is estimate the mean vector and estimate the sigma matrix, and you can estimate from that the regression of any variable on any other set of variables in D. So it doesn't seem like it makes sense at first, but it makes sense because of that fact. So the likelihood, given the probability distribution, still without any missing data, is very simple. You just take the product over the n observations, assuming independence. Now, what do we do if we only observe part of D? Well, we take the likelihood, we're going to assert, what we want is the likelihood function, which are the 2 parameters, mu, which is a vector, and sigma, which is a matrix. Given just D obs, that's the likelihood function. That's the definition of the likelihood function applied to this case. Product over the n observations, but instead of the full multivariate normal distribution, you integrate out the missingness matrices. Okay. Now, it turns out that's pretty straightforward because the marginal distribution of a multivariate normal distribution is normal itself, right? So that's actually great, right? Like so anyway, what you're doing in high dimensional space is you're collapsing over the dimensions where you don't have any variables. If you have two variables, it's bivariate normal. If one is missing for a particular observation, you just collapse to a univariate normal. So it's quite straightforward. The marginals of multivariate normals are normal, it says there. This is simple theoretically because merely it's just a likelihood function for the data and the same parameters as if we had a fully observed mu and sigma, right? So we're estimating the same parameters that we have up here if D were fully observed. This is a little this is complicated computationally because D obs has different elements observed for each eye. So each observation is informative about different pieces of those matrices. So for example, if we have a bivariate normal distribution, and in the first observation we only see y1, suppose there's y1 and y2, we only see y1, well then we're not contributing to the mean for y2. If for the second observation we might have y2, but y1 is missing, and we would not contribute to the mean for y1. And similarly, so you have this kind of crazy another kind of Swiss cheese setup. It's totally possible. It's straightforward. It's just that the means and the mean vector has components that we're going to ignore for certain observations, different observations depending upon what's observed, and the variance matrix has rows and columns that we're going to ignore. Okay, so you'd like some help programming, which we will provide. This also, it turns out, is hard statistically. So statistically, it's a pain. Why is that? So the parameters, the number of parameters of this model increase pretty fast in the number of variables. So if there's p variables, the total number of parameters we need to estimate for this likelihood model, just so that we can then simulate from it and impute, is equal to the number of mu parameters plus the number of sigma parameters. Well, how many are there? Well, there's p mu parameters, right? Because there's p of them, it's a vector, that's how many there are if there's p variables. And then there's this symmetric matrix. So there's p times p plus 1, which is the diagonal, divided by 2, because it's only the lower or upper diagonal. And that's p times p plus 3 over 2, just a simplification. So for example, if there's only 5 variables, then that's 20 parameters. If there's 40 variables, that's 860 parameters. Now you've spent some time watching Optim try to converge, and if you have 860 variables, that's going to be a pain, okay? In particular also, you may not even have that large a sample size. So with 860 parameters, I mean, you're going to get really big uncertainty. So it sort of seems like a big pain. We'll get to it. We'll have ways of much more easily estimating the parameters than sticking it all in Optim. This model is all linear, and it's all normal. It does imply a regression of every variable on every other variable, but it's linear and normal. There are more specialized models to impute for discrete variables and limited variables, such as, in any event, they occasionally perform better, but not usually. So usually it's okay, or it's reasonable anyway, to follow this general purpose linear normal model, even if you wouldn't do this for analysis. So for most social science survey data, which are ordinal scales, 5 or 7 points, or feeling thermometers or things like that, it's a reasonable choice for imputation, even though you wouldn't use it for analysis. Okay. All right, so we need to create imputations from this model. So we have the model, we estimated mu and sigma. Now we have to figure out how to impute from the model. So that we can fill in the DMIS, and then we can run whatever statistical procedure we would have run. So let's figure this out. So suppose D has 2 variables. Again, remember my rule is just to understand something big and complicated, simplify it down to the simplest possible example. So now I'm going to assume there's two variables. If there was only one, we wouldn't be using any other variable to help us impute. So there's two variables. Let's call them x and y. Let's also imagine there's only missingness in y and none in x. Now, as a special case of the big model, D is bivariate normal. So we write it down in the same way, but now we can write it down just as a bivariate normal. So there's two mu's, and there's three unknown elements in the sigma matrix because it's symmetric. Okay, now, conditionals of bivariate normal are normal. Okay, now I want you to understand what that means. Okay, so if you have a bed and there's a sheet on top of the bed, and you take a bowling ball and you put it on the bed, and you fill the whole thing with Jell-O, and then you freeze the whole thing in liquid nitrogen, and then you turn it upside down. Okay, then you have sort of like Casper the Friendly Ghost with the sheet on top of them. Okay, so then you have this bivariate normal distribution. Now we want the conditional normal from that. How do you get the conditional normal from that? So if x is one way and y is the other way, right, and we want y given x, what does that mean visually? What that means is that it's y given a particular value of x. There's a whole set of conditional distributions. Let's just pick one. Let's pick x equal to this value right here. Okay, so we have this frozen Jell-O mold, right? And x just equal to this value. So what do? Well, we take a buzzsaw, bzzz, and another because we're going to make a very thin slice from this. So maybe we get two buzzsaws right at the same time, bzzz, right? And we pull that little section out. We throw away the rest of the Jell-O, and we show it to you. What does that look like? It looks like a normal, right? In fact, it is a normal because conditionals of bivariate normal are normal. That's exactly what it looks like. The conditional expectation function is of this conditional normal is the regression of y on all the x's, right? Because we had one, we sliced out one of these normals, right? But we could slice out another normal and slice out another normal and slice out another normal. So given each value of x, we would have a different normal distribution, which would have the same variance but different means, right? Because it doesn't only have to be a bowling ball. There could be the bowling ball is when they're uncorrelated, but they could be correlated, right? Okay. All right. So just some other details here. The CEF of y given x is a regression. This is the exact formula of the regression. It's got a constant term, which is mu y. So mu y comes from here, and it has a coefficient and a variable. The variable is mu, it turns out minus mu x, which comes from here. Where do we get beta from? Beta is sigma xy over sigma x, which comes from here. Sigma xy over sigma x. So all these parameters, they come straight from here. We've already estimated these, because that's the thing that we estimated when we ran the whole big model. So this is all a result of that. In fact, not only is the expected value of y given x a function of those parameters that we've already estimated, the variance of y given x, which we'll also need, is a function of those parameters too. Sigma y, sigma xy, and sigma x. Okay. So now we'll simulate in order to do imputation. So that is, just to be clear, we have this big Swiss cheese setup. Big data set looks like Swiss cheese. We're going to simulate from this multi-equation model in order to fill in the Swiss cheese multiple times. Then we will do an analysis of each of the filled in Swiss cheese, and with our normal statistical procedures as if there were no missing data. And then we will simulate from that model and create our quantities of interest. But right now we're going to simulate just for the purpose of imputation, not to create quantities of interest immediately. The way we do this is we maximize this multiple equation model. We get point estimates of mu, which is a vector, and sigma, which is a matrix. We then, for the moment, assume multivariate normality by the central limit theorem. Take random samples from these. We're going to improve that, by the way, but take random sample from these, and those are our simulations of mu and sigma. Then we will calculate deterministically the beta simulations and the sigma simulations, right? Because up over here is where we're going to be calculating the point estimates and then simulating from, and then we'll use these formulas, this expected value and this variance formula, to get, by substituting in the simulations of these things to get simulations of the expected value and the variance. We'll draw a simulation then of the missing y, not the expected value of y given x, but the missing y given, from a normal distribution with that conditional expected value and the variance of the expected value. So we're going to use this formula here to do our simulations given the simulated expected value of y and the simulated variance of y given x. This is equivalent to drawing from y equal x beta plus epsilon with estimation, uncertainty, and fundamental uncertainty. It works in exactly the same way. It's just that the only thing we're going to pay attention to from this model is the simulations of y. All right. Now I'm going to talk about the computational algorithms for how to estimate this model, because I don't want you to have to program it all up. It would take quite a while, and even after you did it, it wouldn't work very fast. And so we're going to provide fast, computationally efficient ways of estimating many parameters to make this whole thing work. If you want to skip this section on computational algorithms the first time through, it's okay. You have my permission. You can go right to the what goes wrong section. You don't want to stop here because there's two important topics coming. But these are the computational algorithms. The reason I'm going to explain these to you now, because remember in this class, lots of things we're going to black box when necessary and trust that others have done them right. But these computational algorithms are not only relevant here for imputation, they're also going to be rather relevant for more complicated models. And so you will see them again in this class or more likely in other classes or in other models. And so having a feel for what they are should be good. And so while I'm telling you it's okay to skip this section, I'm trying to give you some motivation to watch it through. So your call. Okay, computational algorithms. Optim is the one that you basically know. It's a generic optimizer. We're also going to talk about EM and EMS. There's 3 pages. This is page 1 of 3. Optim with hundreds of parameters would work in principle, but it would work very slowly, and it might be really hard to get it to really work. There's an idea called EM, which is called expectation maximization. That's what it stands for, which is a fast algorithm just for estimating the maximum. It's much faster than Optim. And the cool thing about it, by the way, is on every iteration, it's known to increase the likelihood function. It may be slower than you want, but it's faster than Optim usually. And every step is a step in the right direction. Here's the intuition. Without missingness, estimating beta is really easy. You just run a regression, no big deal, least squares regression. If beta is known, it's really easy to impute because you just use this very simple equation here, no big deal. So EM works by iterating between the two. And here's what you do. So first what you do is you take some current estimates. Now you don't have any estimates to begin with, so we'll just substitute zeros in or ones or something in for beta hat on the first iteration. Then we create x times beta hat, and we use that as our imputation. But now we have y hat, or at least our current estimate of y hat. Remember I said if you have the y's, if everything's filled in, then you can easily estimate the betas by just running least squares. So that's what we do next. Then you go back, and now that you have a new estimate of beta, you go back to this previous stage, and you impute y hat again. Then you have a better estimate of y hat, and you impute beta again. You keep going back and forth between those two, and that's all EM is. That's a special case of EM. EM actually works much more generally, and you'll see it in other kinds of models. Its characteristic is it estimates the mean. It doesn't estimate the whole distribution, which we will need. Remember, when we use Optim, we find the point estimates, and then we also find the variance-covariance matrix. EM just gives us the point estimates. Okay. We can easily do imputation then via x beta hat plus the simulation of epsilon. That adds some more that adds the fundamental uncertainty. But the standard errors are still too small if you use EM because there's no estimation uncertainty involved. You're just plugging in the beta hat and not reflecting the fact that beta is estimated, has to be estimated, and has estimation uncertainty. And of course, beta hat is not the same as beta. So there's another step we can go, which is called EMS, which is EM for parameter maximization, just as we described, and then we can simulate from it. So here's what happens is you add estimation uncertainty by drawing the beta from a multivariate normal distribution, just as we do previously, only the point estimate comes out of EM, and the variance covariance matrix we just have to calculate by brute force. The central limit theorem guarantees that this works as n goes to infinity, but the problem is that the number of parameters is also going up very fast in the number of variables, and so you might not have a big enough sample for this to actually be adequate. So what that means, what the inadequacy is here, is in EMS. Remember, EMS is a direct parallel to what we've been doing all along. We're assuming this normal works because the central limit theorem applies. So assuming n is large enough for the central limit theorem to hold. And what I'm telling you is that with this many parameters, it doesn't really, you really need a very large sample for this to hold. And so we need to go an extra step beyond the blanket assumption that the central limit theorem applies. And we're going to go that extra step and figure out a better way of approximating whatever the true distribution is, rather than assuming that the central limit theorem applies and it's multivariate normal. So this is called EMIS. And so it's EM with simulation via importance sampling. This was in the first paper, the APSR paper that we did, I listed at the beginning of this lecture. So the idea here is you do probabilistic rejection sampling to draw from the actual posterior or the actual sampling distribution of the betas across samples. How does that work? Okay, let's actually have a look. Let's have a look at it. Okay, so first we have, in one dimension, just to make it simple, so remember I'm going to go to the simplest possible case. So in one dimension we have this crazy distribution, the red one. Let's imagine that red distribution is the one that we care about, okay? So that's the actual distribution. We might like it to be multivariate normal, but it's not, okay? So in this case we'd like it to be normal, but it's not. And so what we're going to do is we're going to take a normal distribution, we're going to scale it up. Remember, because the area under the curve of a proper distribution has to be 1. So I'm going to scale the normal up just so this distribution is encompassed by the normal. So it fits underneath the normal. That's the first step. I'm going to approximate it with the normal. So next step is I have an illustration here with 2 values of theta. So what we're going to do is we're going to randomly draw from the normal distribution, and then we're going to decide whether to keep that draw or not. And we're going to keep them in proportion, we're going to keep them with probability equal to the ratio between the true distribution and the approximating normal distribution. So I did this for 2 values of theta, which we might happen to draw from the normal distribution. So if we draw from the normal distribution and do nothing else and just keep those draws, we will recreate the normal distribution. So instead we're going to do this probabilistic rejection sampling. So here's how it works. Actually, let me give you a simpler case. Suppose the true distribution was truncated at this value. So nothing to the left of this value existed and everything to the right existed. Deterministic rejection sampling means, well, you might not be able to draw from the truncated normal, but you can draw from the normal and throw away any observations that are in the invalid region, to the left of that. So that's called rejection sampling or deterministic rejection sampling. So now we're going to do probabilistic rejection sampling. And as I keep saying, there's 2 values of theta which we might have drawn from a normal. If we happen to draw this one, then we keep it, because the ratio of the height of of the normal that we're drawing from and the height of our approximating distribution are the same. But now suppose we draw this value of theta. If we draw this value of theta, we calculate A and B. So A is the height of the true distribution, B is the height of the normal. That means we drew theta 1 with higher probability than necessary, right? Because it's higher here, right? So what we do is we keep it with probability A divided by B. We literally divide A by B, and then that's the probability, and we decide whether to keep that random draw with that probability by drawing a random number. And if we do that repeatedly, then what happens is the draws that we keep are draws from the true red distribution rather than the approximating normal distribution. So probabilistic rejection sampling is a great way to approximate an unknown, a great way to approximate a complicated distribution that we don't know how to sample from. Okay. All right, next step is we can go one more step and make this simpler and faster. And that's what we do in the next paper. So it turns out that we can use something called bootstrapping. So bootstrapping is very efficient, very, very fast computationally, skips all the approximations, makes different assumptions. Okay, let me explain what bootstrapping is to begin with. So suppose we have the mean of a population. That's our quantity of interest. But what we want is the distribution of that mean. Now, with the central limit theorem, we know the answer. It's normal. Suppose it's a small sample, or suppose we don't want to assume the central limit theorem. We have a sample of 100 people. We have the value of, let's say, income for each of those people. We want to know the distribution across samples. So here's a different way of thinking about it. And the different way is called bootstrapping. What you do is you assume that the only possible values of income are the ones that are observed. Those are the only possible values. That's a massive assumption. It's almost certainly wrong, but it turns out to be useful. Remember, that's our criteria for models. So if we have a distribution of values, a little histogram, and little whiskers, they're called on a graph for where the actual points are, those are the only points we're going to imagine exist. Now let's suppose we want to know what's the distribution of means across samples. Well, if that assumption is right, what we can do is we can draw from the same distribution of actual empirical values. How do you do that? What you do is you take your 100 values, you draw a sample of 100 observations from the same 100 observations. Well, how do you do that? You randomly draw one observation from the 100, you write down its value, you throw it back in the bin, you mix them all up, you draw another value. You write it down, you throw it back in, you mix them up, you draw another value, each one uniformly at random. You do that 100 times, and what that gives us is a sample of 100 observations drawn with replacement. If you didn't do with replacement, we would just get back the original sample. So it's 100 observations drawn with replacement from the original sample. That's one sample. We can get another sample by doing the same thing. We can get 1,000 samples by doing it 1,000 times. We can then calculate our quantity of interest, our estimate of our quantity of interest, the mean in this case, and look at the distribution across all those bootstrap samples. And that's an estimate of the sampling distribution. The variance of that is an estimate of the variance matrix, or in this case, it's just the variance of the quantity that we're calculating an estimate of. So that's the very simple idea of bootstrapping. It works pretty well. You can see it's easy to implement. You don't have to worry about distributions or things like that. It doesn't always work, okay? It is not always appropriate, but it is often appropriate and it often works. When isn't it appropriate, okay? Let's suppose our quantity of interest is the maximum in the population. Well, you'll never observe a value of income larger than what you see in the sample, so it's not going to get there. You're going to need some kind of modeling, like a distribution, for example. So it's not perfect, but it works in a lot of cases, and for the purposes of estimating the variance in big, complicated situations, it's a really fast, easy way of going. So that's what we're going to do. We're going to draw m bootstrap sets of n observations each with replacement from the data. We're going to use EM to just EM, which is fast, easy, doesn't have a variance, but we're not going to need it because we're going to use bootstrapping. So we're going to use EM to estimate beta and sigma, or mu and sigma, to get beta in each one. That'll give us estimation uncertainty because we have an estimate in each one, and we have the variance across the bootstrap samples in the estimates. We're then going to impute dmiss from the model, which gives us fundamental uncertainty. This is lightning fast. It works with very, very large data sets, so it really solves a lot of problems. It was the basis for how we built Amelia 2. So that's exactly this is how Amelia 2 is going to work. It's going to add the estimation uncertainty by using bootstrapping, this idea of bootstrapping. You will absolutely see bootstrapping in many other contexts. Okay, I want to give you a more general way of doing this computational, of estimating the variance. And primarily, I want to give you this because you will see it elsewhere. It's more and more common. And this is MCMC models, or Markov chain Monte Carlo methods. A particular one is called IP, or imputation posterior. And the idea here is it's basically the same as EM, except instead of trying to estimate the mean, we're going to do it stochastically and actually take draws from the proper distributions. So the IP algorithm is repeat the following until convergence, and we get stochastic convergence, which means it doesn't converge to a point, it converges to a distribution. I'll show you what I mean by that. So first there's going to be an I step and a P step, and we're going to go back and forth. So the I step is draw dmiss, that's the thing we're trying to impute. So we're going to draw dmiss from the distribution, the probability of dmiss given dobs, and the value of the parameter. This is quite like imputing y hat in the very simple case. Then we're going to have the P step, which is the posterior step, which will get us theta hat. So we'll draw theta hat from its distribution, given dobs, and the imputation of dmiss we got from here. Then, now we have a better estimate of theta hat, so we stick it back in here, and we draw this. Then we dmiss. Then we take dmiss, stick it in here, and we draw theta. And we keep going back and forth and back and forth. And we repeat this until convergence. Okay. So as I said, IP is an example of Markov chain Monte Carlo methods. It's one of the most important developments in the statistics in like the 1990s and maybe the 2000s. It's still very, very widely used. It has enabled statisticians to do things that they thought would take centuries for computers to catch up and enable them to do. It requires considerable expertise. It is expertise that you absolutely can learn. You can go take a course in Bayesian computation in the stat department or elsewhere, and you can learn to build very complicated statistical models and use this MCMC technology to make them work. Whereas if you just did it by trying to substitute stuff into Optim, it wouldn't work. That might enable you to build models that are more realistic with respect to the features of the world that you're trying to model. And if it helps you learn about the substance, you absolutely should go after it. Okay. There are still to this day relatively few MCMC routines in canned packages, but there are some software packages that will make it easier for you to implement MCMC. You can go after them. They change relatively frequently, but you should just know that they exist. It's important to understand that when you're using MCMC algorithms, they converge stochastically, not deterministically, not to a point, but to a distribution. And so it's hard to know when it's over, right? It's an interesting game. So here's just an example. Convergence is asymptotic. If you ran it to infinity, you'd get there, but we're not there. So you have to do plots like this. These are iterations, and the vertical axis is one of the parameters. So here, as you can see in the beginning, it looks like the parameter value as you're going back and forth between these two steps is, sometimes low, and then it's high, and then it's low, and then it's up here, and it looks like it's staying there, and then it drops down, and then it goes up. But then during this whole period, it looks like maybe over here it converged to a distribution. It's not going to converge to a point, it's going to converge to a distribution, so it's going to keep moving, so it keeps drawing from that distribution. Well, you know, it might be that you do this and then all of a sudden, nope, you know, nope, there's NOP is a technical description. It means it didn't converge here, you thought it did. I actually, years ago in the 1990s, with some really awesome co-authors, built an MCMC model, and we ran it on a set of supercomputers all summer. And we thought we had convergence, and then we thought, let's just run it 2 more weeks. We're all busy doing something else at the end of the summer, and this graph was not an idle drawing. This was roughly what it looked like. Right? We ran it 2 more weeks, and it showed we hadn't converged, and it might not have. Maybe it never converged. So these are called trace plots. Or plot traces. They're hard to interpret. It's hard to know when you're really there. If you have 20 or 100 parameters, it's the worst converging parameter that controls the whole system. So you really have to look at them all. You know, I don't want to scare you away from these things. I just want to warn you about some of the features of it. They are a very valuable technique. Our Amelia 1 used a version of this to make imputations. Amelia 2 is massively faster, and also the code like always works because it's hard to get this to work in a general way. Okay, so here's how multiple imputation is going to work in the style of Amelia 2. We have a set of incomplete data, looks like Swiss cheese, the question marks are the holes in the Swiss cheese. We're going to bootstrap and create 5 different data sets. For each we have bootstrap data with question marks in different places, right? Because they're bootstrap data. We're then going to run EM on each one and create an imputed data set. So we're going to impute deterministically with EM, but given the stochastically generated bootstrap data. We're then going to do whatever analysis method we wanted on the original data. We're going to combine the results either by averaging the means and then doing that thing with the standard errors, or by combining simulations and produce our final result. So this is this tremendously convenient way of doing analysis because it is basically pre-processing, analogous to matching. And once we're done with the pre-processing, we can do run our statistical model the way that we might have originally. Okay. Here's an example just to give you a feel for it of the distribution, the posterior distribution or the sampling distribution of a bunch of different methods. So there's EMB and IP. EMB is EM with bootstrapping. There's IP, there's EMIS, there's also the complete data. If you actually had the complete data, this is a hypothetical simulation, of course. And if you had listwise deletion where it would all be wrong, okay? So everything, and these are 3 different parameters in a particular setup. Next step, we're going to focus on what can go wrong. This, of course, you absolutely want to pay attention to because you don't want it to go wrong for you, and also what you can do about it. The risk, of course, is that we're using inference, and inference is learning facts we have to learn about facts we don't have, and we assume the two are related. With multiple imputation, that problem is very clear because we have this Swiss cheese again, and it might be that the answers to the survey questions have nothing to do with the holes in the Swiss cheese, with the answers that the respondent refused to give you. That's an assumption. That's a basic assumption that you can't get around. You can try to get around it. You can try to figure out what they might have said. You can see if you give them an incentive. Sometimes if they don't answer a question, you say, how about if we give you $1 and we'll see what they answer. You can go try to find other sources of the information. There's lots of things you can do, but the facts you don't have might just not have anything to do with the facts you do have. There's robustness in this method because the imputation and analysis methods are separated. Imputation, the imputation model, the big multiple equation model that we're using for imputation, only affects the missing observations. If you have high missingness, then that's going to be much less robust, because when we impute from dataset to dataset to dataset, a much larger fraction of it is a function of this, this alternative model. So what variables do you include? It's pretty important that you put in at least as much information in the imputation model as exists in the analysis model. You can put more information, but don't put less. For example, suppose you have one variable that you have in the analysis model, but not the imputation model. What happens? Well, having a variable not in a model is equivalent to having it in the model, but having its coefficient be 0. So what you're doing is you're taking some of the observations in your data set and you're telling those observations, and those observations are telling your analysis method that the effect of those variables that you've left out is 0. So what's going to happen if they're not 0 is your answers are going to be biased towards 0. You don't want to do that. You should also transform. This is a multivariate normal model, so you try to make the variables a little closer to normal and linear if you can. So you can transform them to unbounded scales, take the square root of counts, take a probability or a proportion that goes from 0 to 1 and stretch it out by taking its logistic function. You can make a skewed variable like normal, like money. You can take the log of it and make it a bit more symmetric, or like the Box-Cox distribution that I described earlier under the robust standard errors talk. There's lots of other things you can do to get the variables to be roughly linear and roughly normal or continuous. If you have ordinal variables, we're going to assume that the technique is going to assume their interval, so code them as close to linear as possible. Strongly nonlinear relationships, you could use transformations to linearize them, or you can add quadratic terms to the multiple imputation procedure. There's something called uncongenial imputations. The term came from Xiaoli Ming. If the imputation model has as much info as the analysis model, but the model specification is different, you use a different functional form than the linear normal model assumed in the imputation stage, then your confidence intervals that come out of the final analysis will be conservative. That's still okay, but you don't really want them to be conservative, right? So you'd rather them to be accurate, but they're not going to be overconfident. Be careful though, if you're simulating from the last step and you have conservative confidence intervals, the distribution of your quantities of interest are going to be too narrow. So if you calculate certain quantities from that could induce bias. There's a property of super efficiency. When the imputation model includes more information than the analysis model, it could be more efficient than the optimal application-specific model. So let me give you an example. So when you run surveys, you tend to get overwhelmed by the recodes and all the variables. People who design surveys very frequently add in lots and lots of extra questions. That's often a big waste because they tend not to use them. In fact, when you get to the analysis stage, what happens is you say, I'm getting overwhelmed by results, so even though I created 5 measures of this one concept, I'm just going to use the best one or one of them or something like that. So that may be fine for doing an analysis, but in the imputation stage, if you have 5 measures of the same underlying concept, like 5 measures of ideology, where each measure is a policy outcome, gosh, if one of those policy outcomes is missing, the other answers to the other questions, if the person answered 4 out of the 5, would be very useful to make imputations. So you absolutely want to include them, even if you want to exclude them from the analysis model. Okay. So here's a little quiz for you. Just think about things. If X is randomly imputed, okay, so it's randomly imputed, of course, right? Because it's MAR randomly imputed conditional upon the X's, but there's still randomness in there. Is there attenuation? Now, what do I mean by that? Well, if you run a linear regression on one explanatory variable, and that one explanatory variable has random measurement error, then the coefficient on that variable is biased towards 0. As a side point, if you have more than one explanatory variable, the bias can be in any direction. But for that one variable, it goes towards 0. So is it the case, if you're doing imputation, to fill in the Swiss cheese for some of the observations, are you attenuating your coefficients? Okay? So think about that. Now the answer, I need music to play right at this moment, or you could pause and try to think about what the answer is. So the answer is no, it doesn't attenuate the coefficients. Why is that? Well, because what's happening is you have a plot. So you have y and x, and then there's a bunch of dots in the plot. And the dots in the plot is the point cloud, the ellipse, if it's normal, that represents the joint distribution of x and y. If x is randomly, if x is missing, if some of the values of x are missing, then what you're doing with imputation is you're imputing randomly in the point cloud, in the same points in the same probabilities as the point cloud. So the randomness is actually essential because otherwise you wouldn't be reflecting the point cloud. Taking random points out of the point cloud and randomly choosing values from the point cloud and putting them back doesn't actually change anything. So you're actually good. Here's another question, very similar to the first one. So if x is imputed with information from the dependent variable, does that induce endogeneity because of the methodology? And the answer again is no, it doesn't actually induce endogeneity. And why is that? Well, because of for the same reason. What you're effectively doing by including x and y is not changing that point cloud. If you were to change the point cloud, like I showed you for best guess imputation, or right on regression line imputation, and for mean substitution, it changes the point cloud. That would bias things, but this doesn't bias things. Now I'll add one qualification to this. If you want to be completely careful, something for a drug you're going to administer to millions of people, and you want to make complete sure that it's impossible that imputations using y could affect things, because you could affect things if you did things the wrong way. Fine. Just delete. Don't do that. Okay. But under normal circumstances, it's the right thing to do. Okay, and it won't increase your coefficients and it won't decrease your coefficients, so it'll keep it about the same. Okay, draws from the joint posterior, put back into the data, don't actually bias anything. If you do it any other way, you do anything else with the data, it actually will bias things. Okay, all right. List-wise deletion is the thing that we're going to displace here. This is the thing I don't want you to do anymore, okay? And you can do it, offhand as a quick step or something to get a feel for your data, but it's not something you should publish. You should not be publishing with list-wise deletion. So in order to really make that case, let me make the best case for list-wise deletion. Here's the best pitch I can make for list-wise deletion. So if this applies, you should use it, and if not, otherwise. I think you'll find not is what usually happens. So list-wise deletion is better than multiple imputation when all four of the following conditions hold. All four have to hold. First of all, the analysis model that you choose to run is conditional on x, like regression. So that's the first thing. And the functional form we're going to assume is correct. So, and the reason why list-wise deletion is consistent, statistically consistent, and the robustness of regression. Linear regression is amazing. It works amazingly well because it's the best linear approximation to whatever we have. And so, if we have the correct functional form, then we will retain that robustness. That's the first condition. Second condition is there's non-ignorable missingness in X. Now, you wouldn't know that, of course, but you might be able to theorize about it. And there's no external variables that are available in your data set that you could bring in to fix the non-ignorability problem. Because you remember, if you have non-ignorable missingness, if you condition on some more variables, you can make it MAR. So in this case, I'm going to rule that out and say there's non-ignorable missingness in X, and there's no extra variables that you could find to make those MAR. And finally, missingness in X is not a function of Y, so you can't use Y, the information in Y, to impute X. And finally, the last condition that also has to hold for listwise deletion to be better than multiple imputation is that the sample size left after listwise deletion still has to be large enough, right? Because if you threw away all the data like I did when I was in graduate school, or too much of the data, then you're going to wind up with tremendous inefficiency, very large standard errors, and it doesn't really matter whether you've gotten rid of enough of the bias. You're still not going to get anything very useful. So if all four of these things apply, then you should use listwise deletion and not multiple imputation. There may even be something better to do in this case. But these conditions are pretty stringent. They basically say you do not trust the data enough to make imputations for the missing data, but you still trust it enough to do your analysis model. It's a pretty weird situation. Probably if you don't trust the data for imputation, you're not going to trust it to do an analysis model either. But the fact that what we did here is we pushed the method until it broke. This is where it breaks. But since that's pretty far from most of the situations we're in, I would say pretty much most of the time, almost all the time, you should probably just run multiple imputation. Okay, so here's a quick example. This was support for Ross Perot back in the 1996 election. Were voters who didn't share in the economic recovery. The ones there was economic recovery at the time. Some of them were, remained unemployed and stuff like that. Were they more likely to go with a third party? And the data come from the 1996 National Election Study, American National Election Study, with 1,700 observations. And the dependent variable was the Perot feeling thermometer. There's several explanatory variables that researchers are interested in, and a whole bunch of control variables. And then we found some extra variables that would help the imputation, so we could have this property of super efficiency. So if the Perot feeling thermometer was one of the outcome variables, we also put in feeling thermometers for the Democratic candidate Bill Clinton and the Republican candidate Bob Dole, the feeling thermometers for the Democrats and the Republicans, and party ID and various other things. This step is often skipped, but it's a big mistake to skip it. You should really keep it and look for other variables that might help you impute not only your dependent variable but each of the variables that you're interested in imputing. We put in a nonlinear term because we were concerned about the nonlinearity of the effect of age, and we transformed to more closely approximate the distributional assumptions. In particular, we had the number of organizations participating in this election, and we took the log of it. Okay. The analysis model is a linear regression. We used Amelia for imputation. We generated 5 data sets. We're interested in the coefficient on retrospective economic evaluations. Range was 1 to 5. We ran listwise deletion, which is probably biased and certainly inefficient. And the coefficient is 0.43. With multiple imputation, it's a much bigger coefficient and actually a smaller standard error. The effect in going from 1 to 5, we just multiply this 1.65 by 4, because you go from 1 to 5, is 0.66, which is a percent of the range of y. So if retrospective economic evaluations move the whole range, you move the feeling thermometer for Perot by 6.6 points in his favor. So multiple imputation is more efficient, and it shows up with a smaller standard error. The coefficient is 4 times larger. Your performance may vary. You'll see what happens. It worked nicely in this case. Based on listwise deletion, there was no evidence that the perception of poor economic performance is related to support for this third-party candidate, but based upon the multiple imputation estimator, the respondents with negative retrospective economic evaluations were more likely to have favorable views of Perot. So that's the example. Okay, one more topic for this set of slides, which is time series cross-sectional imputations. multiple imputation in time series cross-sectional data, the key thing is everything that we've shown you so far assumes the data have a structure sort of like survey data, where every unit is exchangeable with every other unit after you take into account the explanatory variables. And there's no structure in the data. There's no time series. There's no known set of cross-sections other than the individual people. What if, however, the data look like this? Where the horizontal axis is time, in this case it's years, the vertical axis is GDP, each of these is a country, all the data from these 6 countries and all the years are all in a big time series cross-sectional data set, okay? So what we also can do, and what is programmed into Amelia, which you can absolutely use, it's not hard to do, is respect the structure of the data and include fixed effects, in this case for the countries, time trends, in this case for the years. If you do that, if you do those two, you will get much better imputations. Look at I'm going to get to number 3. Look at the smoothness over time. I mean, there's a lot of change over time, but any one point is pretty well predicted by the previous point. Including that information is really valuable. It might not be coded in any variable other than the year. So we absolutely want to include time trends in this. And of course, the mortality rate, or the GDP in this case, it can be very different from country to country. And so you absolutely want to pay attention to the fact that there's a big shift between different countries, even if the trend over time is similar in different countries. Those are the first two. Well, we can do that in relatively easy fashion. Fixed effects, you put in dummy variables for the countries. Time trends, you could put in a linear time trend, a quadratic time trend. You can put a spline, which is a fit to the a smooth fit to the data, and in order the latter is probably better. But all of them are much better than assuming all your data are exchangeable and there's no structure in the data. And then third, there's one more idea here, which is you can put priors on individual data points. Now this is really important because in these countries, let's look at right here, there might be data missing or right here. Some of those data can absolutely be imputed by the rest of the data in the data set. But in a survey, these are random selections of isolated people from unknown geographic locations. In time series cross-sectional data sets, we tend to know a lot about each of the units. And if, for example, there's no data from one of these African countries in a range of years, well, maybe there was a war going on or a famine going on in those years. We absolutely know a lot about what the data are like in those years. The mortality rates are higher during those two events. We may not know how much higher, but we certainly have important, valuable prior information about those. And so what we showed in this paper, and what is coded into Amelia, is how to put a prior on individual cell values. I showed you earlier on in the course how to put a prior on parameter values. Well, now we're going to put a prior on the expected value of one of these imputations. And if you have qualitative information that goes beyond your knowledge of what variables to put into a model, it can be tremendously valuable. So you can go to qualitative scholars of different regions and areas, and you can ask them questions and interview them about data that's completely missing. They may not be thinking in terms of your quantitative variables, but they absolutely will have lots of knowledge that you can code and put in your model. Amelia makes it possible to put it in a relatively easy way if you take the time to go collect it. So if you have relatively uncertain results, you absolutely want to pay attention to the priors for cell values. Here, let me do it with my other little gizmo here. Pay attention to that, okay? It can be really useful. Okay, let me give you an example of what this looks like. On the horizontal axis here, we have a bunch of data. What we did with these data is we artificially deleted one dot. One of the data points. And then we used the rest of the data to impute. Then we deleted another dot, and we made believe it was missing, and we used the rest of the data to impute. And we kept doing that, okay? That way we can compare the truth, which is the observed data point, with different imputations from these different models. Okay, so first of all, and we did it a whole lots of times, so we can see a confidence interval around what our imputations are like. All for methodological purposes. For substantive purposes, you would choose one of these models, impute once, simulate from the model, calculate your quantity of interest. Okay, in the usual way of doing an analysis, before we included time series information in an imputation model, we would treat the data like survey data, ignore the time series component, except in as much as it was picked up by some of the existing variables. And this is the kind of thing we get. So the green lines absolutely do encompass the true dots, but they lose the trend, right? In all of these, they pretty much lose the trend. Here, the green lines, maybe there's some downward trend in the green lines, like there clearly is in the dot, but you've lost most of the distribution. Here, the true lines are going up and then down. The green lines encompass it. So in some sense, you're not going to make a mistake if you're not going to make your confidence intervals are not going to be wrong. They're going to be very uncertain if you ignore the time series component. But you're going to miss the signal. You don't want to miss the signal. That's what we want to write about. That's where our findings are going to be. And if you ignore the time series component, if you ignore the fixed effects, and although it isn't included here, if you ignore the information in individual priors about individual cells, you'll lose the signal. Don't lose the signal. So the green ones are losing the signal. So then what we did is we included a polynomial, like a squared term or things like that. If you do that, you get the blue lines, right, which very clearly pick up the signal. So, it's great. It really picks up the signal way better, much more efficiently than the green lines. But in addition, we went one step further, and instead of using a polynomial, which makes a parametric assumption, we just fit Loess. Loess is a relatively simple way, you can look it up, it's a very simple way of fitting a smooth curve to a set of points without making a parametric assumption. And as you can see, the red confidence intervals are shorter than the blue confidence intervals, okay? So for each of these. So I highly recommend paying attention to the structure of your data. That's true for imputing missing data and pretty much everything else. Okay, here's another example where the black points are observed and the blue points in the circles are 5 imputations where I have confidence intervals so you can see it with 95% confidence intervals. You can see that, I don't need to tell you what the truth is here, but it seems pretty clear that these imputations are pretty good, and from what we know about the data, it makes sense. So that's the kind of thing that you would see if you fit those models. Okay, so that's multiple imputation for missing data. That's exactly the kind of thing that you should use in your paper. In this course or in other kinds of courses. Missing data is something that if you ignore, just do listwise deletion on average on the basis of empirical behavior that we find researchers follow, you will wind up throwing away about 1/3 of your data. That means that you're going to be, if you're collecting your own data, you're going to be collecting it all, coming back home and throwing away 1/3 of it, or equivalently, you're going to be throwing away several months of your own hard work. I don't see any reason why you should do that, right? Data is very hard to come by, or your time is even harder to come by. Use as much of it as you can in the most efficient way possible. Multiple imputation is, in a certain sense, a really good second best approach that's easier and more efficient and less biased than most other approaches. You can sometimes do better with application-specific approaches, paying close attention to precisely what type of data is missing and under what circumstances, like censoring or things like that. So you might have to go to a different type of analysis, but in terms of a first choice, a simple choice, a choice that will get you roughly the right answer in most cases with accurate confidence intervals, and no bias induced by the missing data procedure, this is quite a reasonable result. I'll mention one more thing, which I did at the beginning. If you have data which are not only missing, but or if some of your data are observed and some are missing, but some have measurement error, then I suggest you have a look at multiple over-imputation, which is also coded into Amelia 2, which you can also use in a very simple way. Instead of only filling in the missing data, you over-impute the observed data, if those observed data or the columns of observed data are deemed by you to have measurement error. So there's ways of correcting for that kind of thing as well. So thanks for listening. We'll see you next time.